Welcome to Oscillations. Today we are going to discuss the free vibrations of the linear triatomic molecule. We will begin by considering free mass points of masses m, capital M and m respectively, connected by springs of constants k and rest lengths b in the equilibrium configuration. So all of these are arranged in a line. And we will begin by looking at the longitudinal vibrations. So by looking at the vibrations along the molecular axis. Then the potential energy has the expression here. And we can cast it in a slightly different form by going to the relative coordinates eta, which are just so these are the coordinates relative to the equilibrium positions of each atom, denoted by x of index 0 and I, for I being 1, 2, and 3 for each atom respectively, and by noting that the difference between the equilibrium configurations is between each atom is this length is equal of b. So by using these transformations in the form of the potential energy given here, we can obtain this expression, and with this so on we can then immediately write the corresponding potential energy matrix or potential energy tensor, which is the one here. Similarly, in these coordinates, the kinetic energy has a simple expression to which there corresponds the matrix here, and having them we can write the secular equation immediately in determinant form here, and if we expand it to obtain the algebraic equation, we see immediately that it factorizes straight away into this form. So it's a very simple evaluation which leads to this expression. So we see straight away that the free frequencies of the triatomic molecule in the case of linear vibrations are the following. One of them is equal to 0. The other one is just the square root of k over m, and the third one is the slightly more complicated square root here. Now if we look at the first one, the fact that the frequency is 0 implies that for this particular mode there is no acceleration. So this corresponds to a situation of neutral equilibrium, which we mentioned earlier on in the discussion. And physically this corresponds to a rigid translation, because this is the kind of motion of the molecule that does not change its potential energy. For this kind of motion, the restoring force is 0, and as such the corresponding frequency of oscillatory motion vanishes. So the molecule does not really have 3 degrees of freedom for longitudinal vibrations, but only 2, as one of these degrees of freedom simply corresponds to the translation of the molecule as a whole along the molecular axis. If you go back to equation 621, you can see there that the frequency can vanish for a positive potential, but not for a positive definite one. So a positive potential is one which can vanish even when not all of the coordinates involved in it are 0. Now our expression 649, which is the one here, implies that the potential can vanish when all of the eta values are equal. So this is the case of uniform translation. Now to remove the 0 mode from the discussion, we can simply ask that the center of mass be stationary at the origin. So if we want the radius vector of the center of mass to have a constant value, which in this case is 0, then the vibrational problem, then we remove the translational mode from the discussion, and the vibrational problem effectively is reduced to one of 2 degrees of freedom. Now, for vibrations in free spatial directions, we deal with 6 rigid body degrees of freedom. We have free translations and free rotations. So for a system having n degrees of freedom, we generally have n minus 6 true vibration frequencies. And all of the zero modes that are involved here can be removed by imposing the conservation of linear and angular momentum on the coordinates. Another instance where zero modes can occur is the one where at equilibrium both the first and second order derivatives of the potential vanish. And in that case, small oscillations may still be possible if the fourth order derivatives are non-vanishing. The third order ones will vanish due to the requirement of stability. However, these small oscillations do not correspond to simple harmonic vibrations. And a simple example of this can be seen by looking at the following question. So let's assume that we have a particle of mass m that moves in a constant vertical gravitational field along the curve defined by this formula. So y being equal with some constant a times x to the 4th power, where y is the vertical direction. So the question is, what is the equation of motion for small oscillations about the equilibrium position? Well, since we know how the curve is defined, we can take its time derivative to find the velocity in the y direction. So then the potential is for a constant gravitational field is just the expression here. The kinetic energy is the sum of the two generalized velocities multiplied by m divided by 2. So if we put all of these things together, we immediately get the Lagrangian here, and the calculation is a bit tedious, so you need to be careful. But if you look at the equation of motion, you should end up with the expression here. So if you take the approximation for small oscillations, right? So you see that it does not correspond to the equation for simple harmonic motion. Returning to the linear triatomic molecule, it is straightforward to find the eigenvectors corresponding to these three modes. So the set of three equations for each eigenvector, for the components of each eigenvector, is given here together with the normalization condition, and it's very straightforward to find the three eigenvectors. The first one corresponds to the zero mode. So this just represents the translation of the molecule as a whole along the x direction, or the molecular axis. So it's a movement of each of the three atoms in such a way that the relative distances between the atoms remain constant and equal with the equilibrium positions. The second mode is the even vibration, or the breathing mode. So it's the mode where the central atom is at rest, and the atoms at the ends of the molecule vibrate together in opposition of phase. So they are contracting or expanding together. And the last mode corresponds to a vibration where all three atoms move in such a way that the center of mass of the molecule remains at rest. Now, normal coordinates can be obtained straight away just by inverting the system of equation 641. So there's nothing really involved here. It's a simple calculation which immediately gives these results. And it should be noted that the zero mode can also be removed by resorting to so-called internal coordinates, and doing so along with the constraint on the motion of the center of mass. So the internal coordinates y1 and y2 have these definitions in terms of the eta coordinates previously defined, and the constraint on the motion of the center of mass is the same as the one given here. And In this representation, the potential energy is the quadratic form here, so it corresponds to this two-dimensional matrix. And you can also write the kinetic energy in these internal coordinates, and you see the potential energy operator is diagonal, but the matrix for the kinetic energy is not. It has a much more complicated expression in these coordinates. And the circular equation, if you write it out, it corresponds to the equation here, which immediately has the following two solutions. So these are just the vibrational modes which we have obtained in the initial treatment of the problem, but as you can see, the zero mode has vanished in this representation. Furthermore, in these normal coordinates, we can also find the normal modes through the exact same procedure as previously, and we will find them to be the two orthogonal modes here. Now, we can assume that at the initial moment, all atoms are at rest, and the outer ones are also at their equilibrium positions, while the central atom is displaced by an amount A0. Then this is the corresponding set of initial conditions written in internal coordinates, and if we use equations 639 and 640, we can immediately calculate the scaling factors for the two modes, and we can find the laws of motion in internal coordinates. And knowing these, we can then immediately write the laws of motion for individual atoms as shown here. So this particular set of initial conditions, we can see it corresponds to vibrations in the odd mode. And in exactly the same way, we can look at a situation where initially all atoms are at equilibrium, but the central one has an initial velocity v0. And then the laws of motion for the internal coordinates are the ones here, and the ones corresponding to the free atoms are those in the list, and once again they correspond to the odd vibrational mode. Another such problem that would involve the vanishing of the zero mode is the problem of the linear vibrations of the triatomic molecule, where the center atom is bound to the origin by an additional spring of constant k. And in that case, if we would want to look at the frequencies of longitudinal vibration, we once again start by writing down the potential, and obviously I'm missing a 2 over here, so the first term is this this distance is squared. So these would just be the first two terms of the original problem, but we need to add an additional term which corresponds to the fact that we have a spring also binding this second atom to the origin. And we once again use the kind of coordinate transformations that we worked out in the original problem, and we should find the potential energy of the form here. So it's the corresponding matrix is this one. The matrix of the kinetic energy will be unaffected, and then if we write the secular equation out, we obtain the following factorized form. So we see that we have, in this case, we have 3 roots, which are all non-vanishing. So we have 3 true vibrational modes, which correspond to the frequencies given here. So the zero mode corresponding to a translation of the molecule is no longer possible due to the fact that the central atom is bound to the origin. Going back to the original problem of the triatomic molecule, we can now look at the more general motion. So we can consider vibrations that are no longer constrained to the molecular axis, but which can also take place in the y and z planes. In that case, the potential energy consists of the original terms for the vibration along the molecular axis, plus two additional terms for vibrations in the y and z directions. And they are written in such a way so as to allow for the possibility of the molecule to rotate about the z or y axis without affecting the overall potential energy. And then using the same coordinate transformations that were applied in the case of linear vibrations, we can write the matrices corresponding to the potential and kinetic energies. So as you can see, this once we allow for vibrations in the y and z directions as well, if we have free atoms to begin with, we are discussing a problem which already has 9 degrees of freedom. So this would be a very difficult problem in principle, but fortunately for the simple potential that we have chosen, it factorizes quite nicely. So the potential energy just factorizes into 3 distinct blocks, and the kinetic energy is diagonal. So it's very easy to write the secular equation down as a product of it factorizes in a product of 3 determinants, and we can solve for each of them separately to find the following resonant frequencies. So omega 1 squared is equal with 0 turns out to be a quintuple zero mode. We have 5 zero modes, 3 of them corresponding to translations along the x, y, and z axes, and 2 of them corresponding to rotations about the y and z axis respectively. We do not have a zero mode corresponding to a rotation about the x-axis, because this would not make sense for a linear molecule orientated in that direction. So these are the 5 zero modes, and then we have the x modes that we had found previously. We have an x mode corresponding to one even vibration, an x mode corresponding to an odd vibration, and we have 2 degenerate modes. So we have 2 modes with the same frequency corresponding to vibrations in the y and z directions, and these are just what these represent is in effect the molecule bending. So it's like a scissor motion. Let's say we have one atom here and one atom here, and the central atom is here. So it would be this kind of vibration where they kind of go like this. And of course, knowing these vibrations, we can also find the eigenmodes, which the eigenvectors, which again factorize quite nicely into 3 distinct blocks, and we have these 3 corresponding to the 3 translational modes. One of them, this one corresponds to the even vibration along the x-axis. These 2, so this one and this one, will correspond to the rotations about the y and z axis, and the last 3, this one will correspond to the odd x mode, and these will correspond to the odd y and z modes respectively. So you can see that if you think a bit about it, these 2 modes in the y and z axis, when they are composed together, they actually correspond to a non-rigid rotation of the molecule. So right, if you have an atom that will be oscillating along the y and the z axis, and you add the oscillations together, you end up with a rotation. So kind of like similar to the case of the Lissajous figures that we discussed back when we studied the central force problem and the harmonic oscillator. Another example where this kind of factorization is really helpful is of the one of a more complicated molecule. So a linear molecule comprised of 5 atoms this time, having the masses listed here in the sequence, and connected by springs of equal constants and rest lengths. We would like to find the eigenfrequencies and normal modes for longitudinal vibrations in the case of the system. So the potential energy for the whole molecule is the one given here, and in order to handle this potential, we need to carry out 2 sets of transformations. First, we have the transformation to the eta coordinates for motion relative to the equilibrium positions, which we have also used previously. We keeping in mind that the differences between consecutive equilibrium positions are equal with these rest lengths b. Then we go to the new set of zeta coordinates that are defined by the transformations here. So when we carry this out, we see that in zeta coordinates, the matrix for the potential energy factorizes very nicely into blocks, one of them being 3-dimensional and the other 2-dimensional. So in other words, we have factorized the 5-dimensional problem into 2 orthogonal subspaces, one of them being 3-dimensional and the other being 2-dimensional. And these 2 subspaces are completely decoupled, also due to the fact that in these coordinates the kinetic energy has a simple diagonal form. And with things written in this way, it's very easy to evaluate the secular equation, and we find the frequencies listed here. So we have a 0 mode, which corresponds to the translation of the entire molecule along the molecular axis, and we also have the non-vanishing vibrations listed here. And if we were to look at the normal modes in the zeta coordinates, we can find them as follows. So we need to look at we have 2 orthogonal sets of eigenvectors, one of them in the 3-dimensional space, the other in the 2-dimensional space. So for the first set, the calculations are a bit involved. We know that one of the eigenvectors needs to correspond to the 0 mode, and is the one given here, and the other 2 can be found from their respective equations, from the normalization condition and from the condition that they need to be orthogonal to each other. And they have the expressions here given in terms of the constants a, b, and c. So keep in mind that the b here is no longer the rest length for any of the springs, it's just a numerical constant equal to this value. So these 3 constants have these values. The calculation is quite a bit tedious, so if you're curious to carry it out, you should check it very carefully and see that these expressions are indeed correct. And for the other 2 eigenvectors, it's a bit easier to carry things out, since we only have a 2-dimensional problem, and their corresponding expressions should be the ones given here. So in summary, we have discussed the 3 vibrations of the triatomic molecule, both with regard to vibrations along the molecular axis and 3-dimensional motion. We have identified 0 modes and how to remove them from the solution through conservation laws, and we have also mentioned ways in which this secular equation can be factorized into blocks that are more easily solved. I didn't mention this, but it was implicitly assumed and considered obvious that these classical models are a great oversimplification of molecular motion. So we have approximated the very complicated electromagnetic interaction between the atoms by classical kind of Hooke's law for springs, but qualitatively the features of the motion remain the same. So for example, the vibrational modes of the carbon dioxide molecule qualitatively have the same features that we have found here when we discussed the triatomic molecule, but of course that in practice to find its to find its real vibrational modes, one would have to apply quantum mechanics. In any case, in the following section we are going to go ahead and look at other examples and applications of the theory of small oscillations by looking at various simple problems. So, with that being said, I want to thank you very much for watching. I hope you found this discussion worth your time, and I will catch you later. Goodbye.